is a brief introduction to our project. We have developed a self-balancing underwater robot powered by the Navio 2 board and Raspberry Pi. The robot utilizes IMU data to estimate its orientation and applies a geometric PID controller to maintain stability in challenging underwater environments. But due to several challenges we have faced, the demonstration would be limited to showcasing PWM outputs corresponding to the changes of the orientation. Here are our objectives: accessing sensor data using PX4 and Navio libraries, designing a PID controller for stabilization, obtaining PWM outputs, debugging and demonstration. Moving on to methodology. First, we installed emulate Raspberry OS, which is compatible with Navio 2. Then, we obtained sensor data using PX4 and existing libraries. After that, we designed Madrick filter to obtain accurate sensor readings. Then, the PID controller was designed. Finally, the resulting PWM outputs were plotted for clear visualization of results. Moving on to results. Here are the sensor data we obtained through PX4 and Navio libraries. It shows the readings from 9-axis IMU, which consists of the accelerometer, gyrometer, and magnetometer. Based on the ROV's thruster configuration shown in this figure, motors 1, 2, 3, and 4 are responsible for yaw control. Motors 5, 6, 7, and 8 are responsible for pitch and roll control. Here's a demonstration of the PWM outputs we have obtained by changing pitch, roll, and yaw. First, we are changing roll in the positive direction. PWM outputs for motors 5, 6 should increase while 7 and 8 should decrease in this situation to achieve stabilization. If the roll is changed in negative direction, outputs should be reversed. Now we are changing pitch in the positive direction. PWM outputs for motors 6 and 8 should increase while 5 and 7 should decrease in this situation to achieve stabilization. If the pitch is changed in negative direction, outputs should be reversed. Finally, we are changing yaw in the positive direction. PWM outputs for motors 1 and 3 should increase while 2 and 4 should decrease in this situation to achieve stabilization. If the yaw is changed in negative direction, outputs should be reversed. So it's clear that our PWM output correctly compensates for the changes in orientation. Hence, it is proved that autonomous stabilization could be achieved by this approach. We encountered several challenges while doing this project. One of the main problems was the Raspberry OS corruption. Due to OS corruption, we were unable to obtain sensor data. We overcame this by reinstalling the Navio OS, restoring full control and functionality of the ROV. Next, we faced several issues due to failure of batteries. It prevented motor power-up, but we were able to generate PWM outputs by connecting to the boards. This allowed us to test the ROV for stabilization without the need to run the motors.